Hello and welcome to the Engineering Dynamics Course Companion, Class 7. We're dealing with kinetics of particles, and today we're going to deal with non-rectangular coordinates. Class 6, we dealt with rectangular coordinates. I am Newt Dog, and this is Wormy, and we are your course companions for dynamics. If you want to, you can go down to the description below and click on links to skip to the example for today. We'll start out with the bottom line up front. Previous class, we had Newton's second law. The sum of the forces, and today's color is purple, you'll notice, are equal to mass times acceleration. These are vectors, right? And we used x and y, and we had the sum of the forces in the x direction is equal to mass times acceleration in the x direction. We defined positive that way, and then the sum of the forces in the y direction equals mass times acceleration in the y direction when we defined the direction that way. Now we're going to deal with path coordinates and polar coordinates, right? Where we have the sum of the forces in the tangential direction equals mass times acceleration in the tangential direction, which we'll remember from kinematics, which I think this was class 4. We can go back to class 4 and see. It was mass times the change in speed with respect to time. Right, so that's like an acceleration along the tangential, right? The velocity is tangential to the path, so the acceleration or the increase in that speed, that magnitude of the velocity, that's that tangential acceleration. But we also have the sum of the forces in the normal direction is equal to mass times acceleration in the normal direction, and that is the centrifugal acceleration. Velocity squared divided by the radius of curvature of the path. Now we also have Newton's second law and polar coordinates, and some of the forces in the radial direction equals mass times acceleration in radial direction. And we'll remember from class 5 that the acceleration in the radial direction has two parts. There's r dot, which is the increase of the distance of the particle from the origin, the point of reference, but also we have a minus, and it's acting in the negative direction from the particle towards that point of reference, and it's r times theta dot squared, right? And you can think of this as the second cousin right here. There's actually a way to find out that those are actually going to have the same magnitudes. But we also have the sum of the forces in the theta direction. We could think of this as the transverse, right? If this is the radial, we can call this the transverse direction. It's equal to mass times acceleration in the transverse direction, and that acceleration in the transverse direction also has two parts. The radius times theta double dot, which is the angular acceleration. It's spinning faster and faster, and it's increasing its speed in the rotation. And then we also have this really strange guy right here where we have r dot and theta dot. 2 times r dot theta dot, and that's the Coriolis acceleration. So these components are really important. I spent a little extra time on this bottom line up front because this will help if you'll recall the context of classes 4 and 5 as they applied to this class 7. Okay, so recall from kinematics, these are that we have in the this is the path coordinates right there. That we could actually we don't draw the path in here, but this is just to help you to visualize what's taking place. Now we put the normal and tangential coordinate axes here. Remember that it's tangent to the path, right? So that's it's supposed to be right there. That's supposed to be the tangential direction. You can see that the forces in the tangential and normal direction, they create mass times accelerations in the appropriate directions. In the tangential, for the force in the tangential, creates acceleration in the tangential. Force in the normal direction creates force in the normal direction. Acceleration in the normal direction. Note here, I decided not to put a weight in here. Let's pretend like maybe we're looking down at this thing. So the weight would be an additional force, but it's not, the path is like curving around and that kind of thing. Right. So here we write down, and this is good practice, to draw the free body diagram, draw the inertial body diagram, and then below it write what those diagrams mean, right? Forces on the left, inertia forces on the right. And one example might be going around a curve, right? Now, that feeling, we often will feel like if we were inside a vehicle, we'll feel like we're being forced to the outside, right? That there's some force pushing us to the outside. That's actually us wanting to continue in a straight line, but by going around a curve, we aren't allowed to go in the straight line. So it's actually the response that we're feeling. We're actually feeling a force of the, let's say you're in the passenger seat and someone's driving around a curve, you're feeling a force of the car pushing you and keeping you and turning you around the path, right? So the centrifugal force we often think is pushing outwards. It's actually the thing that we're inside pushing us inward. Right, so it's a really kind of a confusing thing, but you have to try to work through the math, get some experience with the different problems, and it'll make more sense, right? So you have to just be aware that your intuition might tell you the opposite thing, but remember, you want to keep going in a straight line, but if the vehicle you're in is trying to push you into a curve, that's the force that you're feeling. All right, so in polar coordinates right here, we have all the same things, but let's draw and show up. Now, this object could be doing the same actions. We should point that out. The same motion can be working onto this thing, but instead we can use a different coordinate system to define what's taking place. Right here. So we have an origin that is our reference, and we have the forces in the radial direction, right? Starting from the origin and passing through the center of mass of our, it's small enough that the size of the thing doesn't matter. We treat it as a particle, and that's going to be in the what defines the radial direction. And then by convention, we like to use counterclockwise as positive, so that's why we have E theta unit vector going in that direction right there. And then we write out the equations just like we would, right? And remember, a good example or thing to reference mnemonic is spinning around with Wormy on a string that's on a fishing pole, because it can extend, right? That's the radial direction, whereas the spinning of the chair is the transverse direction. Right there. And maybe if we were to look downwards, we could see, if this thing is increasing, the radius is increasing, it would look like a spiral thing taking place here. So I think I have two examples in this setup. One is going to be for the tangential and normal. So this is going to be a long video. The tangential and the normal direction. And so this is a roller coaster type of thing where we have these brothers again. They were playing basketball, I think, in class 3, but now they've gone to the amusement park. And they're on a roller coaster, and the car reaches 35 miles per hour at the bottom of this curve, right? So there's a curve that's taking place right here, and they're just at the bottom, but they haven't reached the bottom, right? They're still in the curve, right? If they're in the flat area, something else is going to take place. But if they're still in the curve, they still are going to be subjected to this normal acceleration that we're concerned about. The car travels into a 25-foot loop right here, loop-de-loop. So for a 50-pound kid, how much does he perceive he weighs at the bottom of the drop, and how fast does the car need to be traveling around the loop when he gets to the top of the loop so that he doesn't fall out? So like you would still have a harness, but let's say what would be like the minimum speed that you would need so that you wouldn't actually need that harness, right? So we'll start out and by converting the 35 miles per hour into feet per second, right? So we multiply by the 5,280 feet per mile. That's how many feet are in a mile. And then divide by 3,600 seconds per hour, right? 60 times 60, right? 60 seconds, 60 minutes. There you go. Now, the kid perceives that the way the seat is pushing against him. Note that the problem states that the car has reached the bottom of the curve just before the flat portion. So it still is in the curve, but just nearly horizontal, right? So we draw the free body diagram of the kid alone, right? So that we don't want to, often it's important to try to think about what should be in the free body diagram and what isn't right here. So we just want to draw the kid, right? So we do this at the bottom of the drop, right? So this is the same kid. Even though there's two kids in there, we're only looking at one of the kids. So here's the kid on the free body diagram and that same kid on the inertial body diagram. And in this case, the normal is going to be upwards, right? Because that's going to be like, this is the upwards direction remember, he's still in the curve at this point. So we put the center of mass in here. And even though he does have size and shape, his size and shape don't matter to us. So we're still treating him as a particle. He's got a weight that's going downwards, and he's got a normal force. And I didn't draw it on his seat, but that's what he's feeling like the seat is pushing up onto him. And there's also some tangential force that would be moving them along. It could actually be in the opposite direction. There should be there could be some, for instance, that could be the back of the seat pushing against him, or it could be the harness that's pushing in front, right? I went ahead and drew it in the positive direction because we're not going to actually use it for anything. So we just assume that the only acceleration that we care about is in the normal direction. So in the normal direction, the sum of the forces, I write them out, is mass times acceleration. And we take a look at the only things that are happening in the normal direction are that normal force and the weight, right? So we know his weight. We can find his mass. His mass is going to be the 50 times 32.2. And we know what the velocity is, 51.33. So that normal force is 118.2. So even though he weighs 50 pounds, it's going to feel like, as if he was somewhere not on the moon, but someplace with larger gravity than Earth, right? He's feeling like he's much heavier, and that's going to be really the seat pushing back up onto him, right? So 118 pounds. So now let's also take a look at the top of the loop, right? So we want to take it's really the minimum speed, so he stays in the seat without a harness. And so we draw him again, but this time he's upside down. And so also the normal direction is changed, right? The normal direction is now right here. Remember that the normal and tangential directions follow the particle around. So the weight now is going downwards, and the force in the tangential direction is still pushing him this way. It could go the other direction too. We're not dealing with that portion of it right now. And I'm drawing in the normal force that's actually here, but actually we're going to see in a second, that's going to be 0 right here. So here is the direction of the acceleration is going to be towards the center. We know that. And then we write this out right here, but we take the normal force as 0 because that's going to be the minimum, right? If it was a positive number, that would mean that he's being pushed down this way right here. We really would want maybe to draw a harness, right? If there was a harness on here, he would have a force upwards right here that's keeping him in the seat if it wasn't going fast enough to cause him to be pushed up onto the loop. But so the minimum speed right here, we're able to find by solving through this right here. And we find that it's 40.12 feet per second, or 27.4 miles per hour. Now, notably, this is kind of impressive. That weight of him would actually cancel out. That happens. Want to be on the lookout for that. That actually happens in lots of different dynamics problems where it turns out it didn't matter. That speed was that speed, regardless of what size of a kid is in that seat, and that's counterintuitive as well. So you want to be on the lookout for this type of thing. Now, okay, so here's going to be another example because this class has path coordinates, but it also has radial components or polar coordinates. Now, this is a much more difficult problem where we have Newt Dog, me, and we have Wormy on a kite string. right? And so I'm running along and the kite string is spooling out, right? So Wormy weighs 0.2 kilograms. So now we're dealing with SI, and Newt Dog is accelerating by 4.5 meters per second in that direction, and traveling at that instant at 1 meter per second. The kite is at 25 degrees from the horizontal, right? So this right here is the 25 degrees. And it's increasing, right? So it's increasing this way by theta dot of 0.25 radians per second. That angle is increasing, and that it's even getting larger and larger, accelerating by 0.1 radians per second squared. And the kite has a string tension of 40 newtons and is 5 meters long at this point, right? And is spooling out at unspooling, I should say, at 0.5 meters per second, right? So it's coming out of here and it's coming in that direction at 0.5 meters per second, right? Those things are getting in the way. And but it's not, it's getting like it's going out, but it's slowing down. The rate of it spooling out is slowing down. So what forces are being exerted on the kite, by the kite on the apple, right? So that kite is being pushed out here because of wind resistance, right? Being pushed away, or maybe it's out that way with the way the camera is oriented right here. So there's forces of the string being pulled onto the apple, and there's forces of the kite pulling in the other direction, and there's weight going, and poor Wormy, he's getting all kinds of forces, stuff put onto him. So I think I drew all this stuff on here, and now my marks are getting onto the thing. So let me clean that up. Okay. So, and also I label Newt Dog as point A and Wormy as point B. Right. So some of the things that are happening is that Newt Dog is moving. So there's relative motion here too. Newt Dog is moving at a particular speed and with a particular acceleration, but also Wormy is moving with a speed and an acceleration, and they're moving relative to each other. Right, so everything that's happening between the spool and the kite is like a relative motion, whereas there's also an absolute motion of what's taking place here, right, between the two things. So there's a lot going on. So let's just tackle the things that we know. We know that there's a lot of polar information here, so we want to summarize what the variables of interest are. Right, we've been presented with that in the problem, and getting the correct signs in there. Right. I decided to make positive is counterclockwise right here. So that means, because it's going clockwise, that we're going to make that negative. We also, it's slowing down, so our double dot is negative. The acceleration is described in polar coordinates, and it's referenced. So this spool is really the reference point for that polar coordinates. And so we could write out what the acceleration is, but this is the relative acceleration of B with respect to A, right? And we can plug all those things into this relative acceleration, and we can find what those components are for this relative acceleration. And in order to add them together, right? So there's acceleration of Newt Dog was given here. It was also given the velocity of Newt Dog. That was the 4.5 and the 1 meter per second, right? So in order to combine these together, we need to transform one of them. We need either transform the radial into the polar, into x and y, or we could take the x and y, or really just x direction, and turn it into polar right here. All right. So we take the we're very careful about this, but we take the angles and the coordinate axes, the unit vectors, and we superimpose them, and we make a transformation matrix, just like we did in class number 4. Right, so if you're not familiar with how we did that, make sure you go through this. And we had to make some decisions about what angles we're going to use. I decided to use that 25 degrees that we had in there as the what I defined as theta. And you could see why some of them are negative and and only one of them is positive. And which ones are cosines and sines depends on what orientation you decide to use for the thing. So applying that acceleration, that 4.5, we're able to find what the acceleration of A is going to be. So now if we're going to do an analysis, the kinetics, we really need to only look at the acceleration of B. Right, so that's what we were going through right here. The acceleration of B is going to be equal to the acceleration of A plus the acceleration of B with respect to A, right? And now we're able to get the total acceleration of B, these values. And we draw the free body diagram of the apple. That's all we care about. And we put in our coordinate axes, and we define here's the weight of the apple. We have the force due to tension, which we were told, and then we have a force in the radial direction and in the theta direction. And I decided to go ahead and draw that upwards. A lot of times if I don't know the direction of something, I will choose the positive direction and then see what happens. But here I made the call to decide that it must be in the theta direction, that component is. And we're accelerating in the radial and the theta direction right there. So so when we plug these numbers in, we have to decide what is going to be positive. We have to be very careful about what we've defined as positive. But we know that we already had made that decision right in here, right? And we plug these in, and we find in the theta direction, we have 2.309 newtons. And in the radial direction, we have 40.32 newtons, right? And we're very careful as we're drawing these, writing these things out, that on the left-hand side are the forces, and on the right-hand side are the inertial forces right here. So we have the total force that is acting on them. But quite often we'll want to know some results in X and Y. We just like rectangular coordinates. It's probably, we think better in terms of them. So we do another coordinate transformation. And so in this time, we go from ER and E theta to I and J. So if we're doing that, what we do is we take that ER and now we go by the row, right? So there you go, where we have the negative cosine and the positive sine. So I'm wondering if I got this wrong up here. I gotta wonder if I got this wrong. I might have made a mistake. It's known to happen right here. I gotta decide when I'm going here. I think that right there should be positive. And then let's take a look at this other one when I go for the, I'm going to take the E theta. So that's this. No, okay, I see what I did. Okay. I didn't make a mistake. I just jumped ahead like one step right here, right? So I took this 40, which is the ER, and multiplied it by, and I took this thing and I multiplied it by this, and then I took this thing and multiplied it by this. Yes, that's correct. And then I took this and multiplied it by that, and then I took this and multiplied it by that. I think it's easier. I skipped a step. I don't like skipping steps, but it's easier, I think, to just go in the columns or rows mindset. All right. So anyway, we want to be careful with that transformation matrix. Now we also like to know the magnitude of stuff, so we'll find the magnitude, and then we could also find the angle, and this is with respect to the x-axis, right? So we're able to find out that's the sum net force that's being applied by the kite onto the apple. All right, so the long example problem. So for more examples, and that's some of the mentality behind the book, I wanted to make a book that has more in-depth and difficult examples. Because I felt that students often complain that the examples are in other books are perhaps a little too easy, and then the homework problems are much harder. I don't want you to go searching for an identical homework problem to the one that you have, because then you won't learn things. But I think by seeing a more challenging problem and picking it apart and then having a long detailed explanation about the thought process is one of the important ways that we learn. At least I think that's how I learn, and hopefully this will benefit you. So for more examples, and I've included more examples in here. Let's see, how many examples do I have in example in class 7? Oh, there's quite a few more. Let's see. Okay. I also do tie in some of the other topics right here. Oh yeah, we go around a curve. Yeah. Oh yeah. Oh, I'm also playing a little bit of tetherball, which is probably not something that was in there. So anyway, in the next class, this was kinetics with Newton's second law, and in the next class we are going to deal with work and energy. Check out the links down below in the description for how to get the book from the Morgan and Claypool Publishers website. Also, please subscribe to the channel. Give me a like if you liked it. Please go ahead and put comments down into the comment section. I welcome. So thank you very much, and I hope you'll join me again for another Course Companion Dynamics session.